Hello, folks. So this week's module is a bit of a two-parter. So this first lesson is going to look at issues of probability and probability theory. And then there will be a separate lesson that is on sampling distributions and different sampling methods. So stay tuned for that one. There's two this week, but both are relatively shorter than usual. So it kind of made sense to do both of these within one module because they're both shorter ones. So this first one, before watching this lesson, you should have read the PDF, the Fitzgerald and Fitzgerald, pages 167 to 176. This week's lessons are ones that I generally really like our textbook. The only stuff I don't think it does well is the stuff that we'll do in this module. That's why there's these supplementary textbook readings instead. And you'll see that compared to our textbook, the readings for this week are a little denser and a little tougher because they're from other textbooks, but maybe that shows just how great our textbook is in terms of breaking things down in simple ways, because I know these ones are a little tougher, but we'll work through it now together in a way that should be manageable. Okay, so when we say probability, what are we talking about? Probability is the relative frequency, so think what percentage or proportion of times something happens or is expected to happen. And some important terminology here includes what's called an outcome or an event. And an outcome is the result of a theoretical random experiment. So that means if we are doing things like rolling a dice, or rolling a die, or pulling out lotto balls, all of these things that we know actually happen at random, the outcome is what happens as a result of doing that. So do we flip a coin and get a heads? Do we roll a die and roll a number one? You'll see that a lot of what we talk about in this probability lesson are thinking first about things that actually we know occur at random. That's the best way to kind of understand probability, by looking at things that we know actually do happen randomly and that aren't influenced by something else. So we'll talk a lot about these examples that involve rolling dice or flipping a coin or pulling out lottery balls or coins from or numbers from a hat because these are actually random events with random outcomes. The second term here is theoretical random experiment, also known as a trial. So this is some imaginary activity whose outcome is due to chance. So everything that I just mentioned, like rolling a die, having, my 4-year-old plays Chutes and Ladders now with one of those little spinners that lands on a different number. Those are all examples of theoretical random experiments, things that actually happen due to chance. So to kind of give a real world connection and how this will all start to matter for inferential statistics is, let's say we had a survey question that asked, what's your favorite color? And we gave the 4 response options here, right? People could pick from red, blue, green, or orange. If there was really no pattern in people's preference of favorite color, the probability or the likelihood that somebody selected red would be 25%, right? 1 in 4 is 25%. Also a 25% chance that somebody would like blue and green and orange, right? That these would all be probabilities of 0.25 or 25%. But what if we had a research question that was saying, does age influence color choice, right? So age would be our independent variable, color choice would be our dependent variable. So perhaps we were studying the effects of age on your favorite color, and perhaps kids are more likely to like the color red than the other colors listed because, I don't know why, because fire trucks are red and kids like fire trucks, or red's a really popular color with kids, whatever the reason, right? We would be able to say, okay, if instead 40% of kids like red instead of the 25 we would expect, is that difference in probability evidence that our independent variable actually does influence our dependent variable? Is it evidence that age impacts color choice or color preference significantly because that 40% of kids who pick red is substantially more than the 25% we would expect if color choice was just random. So that's where the kind of connection to real world statistics will be getting to. And again, like all of 302, Soc 302, the second statistics class will actually be doing those statistics. But for our purposes now, we're going to be kind of going through these random fictitious thought experiments using things like die and coin flips, etc., so that we get this idea of probability first. Then we can say, like, okay, here's how we do it with real world social science examples. One other thing, though, I want to say about this idea of probability theory. So today's lesson is a lot of conceptual looking at rules of probability. So probability theory is all about determining the likelihood or the probabilities of certain outcomes from theoretical random experiments given certain assumptions. So that means if we flip a coin, what are the rules for which we determine how likely we are to flip a heads versus a tails? That's what it means by what are the probabilities of outcomes for these theoretical random experiments. What's important is that it doesn't tell us, right? Probability is not a magic wand or a vision into the future that tells us what outcome will happen in any given trial. It doesn't tell us in one coin flip if we will land on a heads or a tails, but it does tell us what's the proportion of times any outcome is expected to occur. So it'll tell us the likelihood that an outcome happens, not which one will certainly happen in real life. Okay, so we'll look first, these first set of rules we'll go through are rules for outcomes of a single trial. Single trial just means we're doing something once. We flip a coin once, we roll a die once, we pull a lotto ball out of in a lottery once, right? Single trial just means we're doing something once. And there's rules of probability for single trial, and then there's separate rules of probability for multiple trials. So we'll look at multiple trials second. All right. And so let's make sense of, I know that these rules as they're given in the reading are in kind of like dense language, so let's work through this. Number one says, the number one rule is that there must be an exhausted list of all possible outcomes of a trial. So that just means we need to know what, in order to figure out the probability that anything, one outcome happens, we need to know what are all of the possible outcomes. We need this exhaustive list, meaning all possible outcomes need to be known. So for example, if we're rolling a die, we know there's 6 possible outcomes, right? You can roll a 1, you can roll a 2, a 3, 4, or 5, or 6, right? If you are flipping a coin, there's 2 possible outcomes, heads or tails. Rule number 2 is that the possible outcomes must be mutually exclusive. They have to be one thing or the other thing, right? So we can't say it's possible to roll a die and get both a 1 and a 6 at the same time with one die, right? Mutually exclusive means it's one or the other outcome. If you have some funky thing that's not mutually exclusive, then all of these rules of probability, of identifying probability for single trial, don't apply. Rule number 3 is that none of the possible outcomes can be assigned a probability larger than 1 or a probability less than 0. A probability of 1 means that the outcome is certain to happen, that it's absolutely going to be just one outcome, one thing that's the result. A probability of 0 means that the outcome is impossible, right? In all of the examples we'll look at, the probability is somewhere between 1 and 0, right? If you flip a coin, you have a 50% chance of getting a heads. That probability then is 0.5. If you roll a die, you have a probability of rolling a 6 1 out of 6 times. 1 divided by 6 is 0.167. So all of these probabilities are somewhere between 0 and 1. Rule number 4 is that the probabilities assigned to all of these outcomes, right, everything we talked about for the previous rules, to the mutually exclusive, exhaustive possible outcomes in a single trial must sum to 1, must add up to 1. That just means that if we have an outcome for the probability for each of those outcomes, and we added up each of those, it's going to add up to 1. So if for flipping a coin, you have a 50 shot of getting heads versus tails, right? 50.5 plus 0.5 equals 1. Rule number 5 says the probability of getting one or another mutually exclusive, exhaustive, independent outcomes, right? That's fitting in all of the previous rules. The probability of doing this, of getting one or another outcome, is the sum of the probabilities of each of those outcomes. This is the one that we'll use to do actually some math for this lesson, right? This one says if we want to know what's the probability of getting one outcome or another outcome, the way you figure that out is by adding together the probability of getting this outcome to the probability of getting that outcome, and that tells you the probability of getting one or the other. We'll see that for single trials, I'll ask you to identify if it's a single trial problem by saying, is this an or question or is this an and question? If it's asking about what's the probability of getting one thing or another thing, then we know that we're adding together the two probabilities. So for example, if you're rolling a die, the probability of getting any one of those values, of getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6, is 1 out of 6, right? You have a 1 in 6 shot of rolling any of those outcomes. 1 divided by 6 is 0.167 or 0.1666667 into infinity, right? So we can round to 0.167. The probability of getting a 5 or a 6 then is just the sum of the probability of getting a 5 and the probability of getting a 6. So the probability of rolling a 5 is 0.167. Probability of rolling a 6 is 0.167. So rule number 5 tells us if we want to find the probability of getting one or another, we add those two together. So if we wanted to ask, and this is just kind of like a fun little graphic for looking at the probability of rolling a dice or rolling a die, is to think about the probability of getting a 1 is 0.167. Same thing for all of the values, right? The probability of getting any value is 0.167. This shows that 0.167 times 6, right? Add up all these 0.167s. We sum to 1. That's the rule that says all of the mutually exclusive outcomes have to add up to 1. And then a practice problem would be, the classwork problems, the homework problems for this lesson will be something like, what's the probability of rolling a 1 or a 5 in one roll, right? So one roll is telling us that we're looking at the rules for single trials. We're doing something one time. And we know we figure out the probability of getting one outcome versus another outcome, one outcome or another outcome, by just adding together the probabilities for each. And sorry, I don't know why the graphic goes away when I give you the answers there. But so the probability of getting a 1 is 0.167. The probability of getting a 5 is 0.167. If we want to know the probability of getting one or the other, we add them together. Then we can ask, what's the probability of rolling a 1 or a 2 or a 3 in one roll? Again, if it's asking you the probability of doing something in one trial, right, like one roll, we know that's the rule for single trial that applies. Now we're just adding together the probability of getting a 0.167 is the probability of getting a 1, 0.167 is the probability of getting a 2, 0.167 is the probability of getting a 3. Add those all up, and it's, right, a 50-50 shot of getting 1, 2, or 3 in one roll. Okay, so I don't know why that graphic's all funky. Hopefully this one doesn't do the same thing. Okay, let's use as another practice example, let's say we have a spinner. Here is now my son who's playing lots of chutes and ladders. I see this a lot. We have a spinner with 5 different values, right? What's the probability of getting any one value? Is if there's 5 values, the chance of getting one value is 0.2, right? You have a 1 and 5, divide 1 by 5, and that's 0.2. You have a 0.2, a 20% chance of landing on a 2, a 20% chance of landing on a 4, etc. So if we wanted to know what's the probability of spinning a 1 or a 4 in one spin, doing it in one spin is telling us we're looking at single trials. And the probability of getting a 1 is 0.2. The probability of spinning a 4 is 0.2. We add them together, and that tells us the probability is 40% or 0.4 for spinning either a 1 or a 4. Then we can ask a second problem. What's the probability of spinning either a 1, 4, or a 5 in one spin? Just like the previous one, probability of spinning a 1 is 0.2, probability of spinning a 4 is 0.2, probability of spinning a 5 is 0.2. Add them together and we can say you have a 60% probability of a 60% chance of getting a 1, 4, or a 5 in one spin. Okay, so that's single trials. Rules for outcomes of multiple trials now. This just means we're doing things more than once. So this is spinning two or rolling two die or two die twice, flipping a coin multiple times, having a lottery ball situation where you're pulling out multiple balls. Multiple trials just means we're looking at more than just one event. What's important for the rules that we'll cover for multiple trials is we're keeping it simple. We're only going to look at rules for what are called independent events. So that means for an independent event, the probability of all possible outcomes don't change from trial to trial. This is largely an issue related to replacement. So the most straightforward way to think about this is we know that when we flip a coin, the likelihood of getting a heads or a tails doesn't change from coin flip number 1 to coin flip number 2, etc. Right? That the probability of getting heads is 0.5 the first flip. The universe, this is, relates to this idea of the gambler's fallacy. The universe doesn't keep track of how many heads you get in a row. It doesn't matter if you flip 10 heads in a row. That 11th coin flip, your chance of getting a heads is still 0.5. It's not more or less depending upon what you flipped so far, right? That does not change. What's most important is thinking about with examples like, let's say we had a bowl of lottery balls. Each one is labeled 1 through 10. The chance of pulling out any one value, any one ball, is 0.1, right? Is 1 out of 10. The probability, so let's say we want to say the probability of pulling out a number 6. We pull out, we do one pull out for a ball and it's not a 6. If we keep that ball out of the bowl, if we don't replace it, the probability then of pulling a 6 is no longer 1 in 10, it's now 1 in 9 because we've removed one of those balls, right? That would then be an example of a dependent event where probabilities of certain outcomes do change from trial to trial because we are sampling without replacement, right? We've taken something out and we've not put it back in. For our purposes, the rules of probability for dependent trials get super complicated outside the scope of what we need to cover. So know that all of the rules we're looking at are for independent events, meaning that there's random sampling with replacement. The probability of getting any one outcome does not change from event to event, from trial to trial. Okay, sorry, I talked ahead a little bit here, right? This is in writing everything for multiple trials. We're doing things multiple times. We're examining 2 survey questions, rolling 2 dice at once, rolling 1 die multiple times. And so for these ones, we're not interested in the probability of getting one outcome or another outcome in one attempt, that's single trials, but rather we're looking at the probability of getting one outcome and then another outcome in the next trial, right? So in identifying these problems, as we're doing the practice ones, the first step, and I'll explain this when we look at the classwork problems as well, is to ask yourself, is this an or question or is it an and question? If it's an or question where I'm looking at something and saying, is it a likelihood for me to get this or that? then we know we're adding the probabilities together. That's for single trials. If though it's a question that's asking you, what's the probability of getting this outcome and another outcome, that's multiple trials, and we'll see then we're using multiplication with that rule. So the or versus the and question can be really helpful in thinking through how to do the right steps with the math to get the answer. Okay, so now continuing with the numbering of the rules for outcomes of multiple trials start with rule number 6. And I will explain again too that I've given these rules numbers. These are not like statistically decided that statisticians refer to like this rule as rule number 6. I've just found with students in the past, it's helpful to be able to identify, have some type of number associated with each rule. So don't go on to 302 and you have a different professor besides me and tell them like, oh, well, rule number 6 of probability says blank. They won't know that that's rule number 6, right? That's not a real thing. Just for our purposes of learning, numbering them, I found to be really helpful. Okay, so what does rule number 6 say? For multiple trials, this says that the probability of getting any specified combination of outcomes in a series of trials whose outcomes are independent is the product of the probabilities of getting each of the outcomes in a single trial. I know that's a mouthful for this rule. All that's essentially saying is that if we want to know what's the probability of getting one thing and then the next thing again separately, we multiply, that's the product, we multiply the probability of getting each. So if the most straightforward example we can do is, what's the probability of getting 2 heads in a row for over 2 coin flips, right? So first we identify in our brains, if we see this question, we know that this is multiple trials because we're doing 2 things in a row. It's not just doing something once. So we're thinking now the rules for multiple trials apply. And we know that this is an and question because it's asking if we get a heads and then another head, right? 2 heads in a row is an and question, not an or question. It's not saying over 2 coin flips, what's the chance that we get a heads in the first or a heads in the second? No, it's saying what's the probability of getting 2 heads in a row? So a heads and a head. And so the probability of flipping a head in one flip is 0.5, right? 1 out of 2. So to figure out what's the probability of flipping 2 heads in a row, we multiply each of those probabilities. We multiply 0.5 times 0.5 to get 0.25. So you have a 25% probability of flipping 2 heads in a row with 2 coin flips. Another example could be, an example problem could be, if you have a bowl with 5 balls in it, each ball is labeled with a number between 1 and 5, right? So one has a 1, one has a 2, one ball has a 3, one has a 4, one has a 5. What's the probability of getting a 4 and then a 5? So the first step is to figure out what's the probability of pulling out any one number. And the probability of getting any one ball is 0.2, right? Is 1 out of 5. You have a 1 out of 5 shot of pulling out a 4, and you have a 1 out of 5 shot of pulling out a 5. Because this is a multiple trial question, right? This is an and question. The probability of getting one thing and then another, we know we multiply those 2 probabilities. So 0.2 times 0.2 is 0.04. So it's actually only a 4% chance that in 2 draws and 2 pullouts, you're going to get a 4 and then a 5. One of my favorite things about this lesson is that students realize how difficult it is to win the lottery, right? That if for this, you had only 5 numbers, right, and 2 chances, and you want to get a 4 and then a 5, that's only a 4% chance of doing that. Multiply that by how many numbers are used in the real lottery, and you see how difficult or how low the probabilities would be. Okay, last slide here. Last thing is, what's the connection here to inferential statistics, right? How does this help us at all in terms of doing the more sophisticated statistics that will be coming. And this is what I started to talk about in the beginning, right? How do we know that anything is actually influenced by the independent variable versus just something that happens due to chance? So much of inferential statistics is about what would our outcomes look like if there was no independent variable influencing them, if it was just totally due to chance, and we compare that to what we actually observe with the independent variable in play. And if that difference is big enough, then we can say, okay, maybe the independent variable is the thing that's making this outcome different than what we would expect due to chance. So the first example I have here is about perhaps you roll a die 10 times and you get 10 sixes in a row. This might suggest that there's actually something wrong with the die because that's so rare, right? The chance of rolling 10 sixes in a row is perhaps the independent variable is that there's something wrong with the die, that it's loaded, that it's weighted to make one outcome more likely than the other. So all of inferential statistics is about comparing what's called the observed, what actually happens, to the expected. And the expected is what happens if probability theory was in play and the outcomes were just due to totally random chance. So all of inferential statistics builds models using probability theory and then compares them with real world observations, right? So go back to the question that I gave in the beginning about favorite color. If we see that a certain population answers that their favorite color is green at a higher percentage than all of the other colors, how big does that need to be for us to be able to say, oh, there's something about this population that causes them, that influences them to select green? Because we know due to chance, it would just be 25% of people like green. Okay, so stay tuned. We'll have lots more practice problems on doing the and versus or questions. When do you multiply versus add the probabilities? Those will come up in the classwork. All right, I'll talk to you guys soon. Stay tuned for, remember, part 2 of this lesson is on sampling distribution.